Welcome to this explainer. I want you to imagine, just for a second, that your body is this vast, heavily fortified city, right? Most of the time, the gates are locked, the walls are high, everything is running smoothly. But suddenly, there's a breach. A microscopic invader slips past your outer defenses, and boom, your city is under siege. Now, we've all heard of antibodies. They're the elite, highly trained special forces of our immune system that take out threats with absolute precision. But here's the catch, and it's a big one. It takes almost a full week for your body to actually manufacture those antibodies. So what happens in the meantime? How on earth does our biological city survive that agonizing 7-day gap before the cavalry finally arrives?
So let's dive into this life or death vulnerability gap, because it really is a fascinating question. If we literally have to wait a week for our specialized defenses to show up, why doesn't a rapidly multiplying infection just completely overwhelm us by, say, day 3? To get a handle on this, let's look at a truly terrifying invader, Streptococcus pneumonia, or just pneumococcus, as it's often called. It's the most common cause of community-acquired pneumonia, and it's nasty. It can strike totally out of nowhere or just hitch a ride right after you've been weakened by the flu.
And this particular bug is an absolute master of evasion. Its main weapon, its virulence factor, is this incredibly slimy carbohydrate capsule that wraps around its cell wall. Our frontline predatory white blood cells, the neutrophils, they rush in and try to grab it, but they literally can't get a grip. It's kind of like trying to grab a wet bar of soap in the shower. The pneumococcus just bounces right off. So without our specific antibodies ready to hook onto that capsule, these bacteria are just free to multiply and ravage the lungs. I mean, in the days before antibiotics, this fast-moving infection was incredibly deadly. And this brilliantly highlights the critical difference between the two main tiers of our internal defense system. On one side, we've got our antibodies. Think of them as incredible, precise snipers. They are highly specific to a single target, but agonizingly slow to deploy. Like we said, almost a week. On the other side, though, we have our rapid deployment first responders, the acute-phase proteins. These guys are crude. They have a really broad target area, but their superpower is that they act immediately. They are the emergency backup system keeping us alive while the snipers are still getting into position. To really appreciate how we figured out this amazing backup system, we've got to rewind to the early 1930s at the Rockefeller Institute in New York. Two researchers, William Tillett and Thomas Francis Jr., were desperately trying to find a treatment for the pneumococcus crisis. This is way before antibiotics, remember. The standard treatment back then was actually taking blood serum from a patient who had just survived pneumonia and injecting it into someone who was newly sick. But they stumbled onto a total medical mystery. They found a substance in the sick patient's serum that was attacking the bacteria, but it wasn't an antibody. It didn't care about the specific strain. It attacked all of them. And the weirdest part? As soon as the patient got better, this mysterious substance completely vanished. They named this heroic first responder C-reactive protein, or just CRP. As it turns out, your liver produces CRP, and it acts almost like a biological heat-seeking missile. But instead of looking for a specific bacterial capsule, it scans for something way more common, a simple chemical called choline. Choline is everywhere. It's in us, it's in bacteria. But don't worry, CRP is highly regulated. It only switches on to clean up exposed choline from our own dying cells when tissue gets damaged, or it attaches to the choline on the surface of bugs like pneumococcus. By hooking onto the bacteria, it essentially ruins their slippery little defense and shuts them down. And this kicks off an absolutely wild biological chain reaction. First, the second an infection starts, distress signals called interleukin-6 sprint straight to the liver. Next, the liver flips the emergency switch and starts pumping out massive amounts of CRP. Third, this CRP floods into your bloodstream, hits the battlefield, and binds tightly to the exposed choline on the bacteria. And finally, this is the best part. Our predatory white blood cells, the neutrophils, can now easily grab this tagged invader and just devour it. They phagocytize it, destroying it entirely. It's literally microscopic execution at its finest. But look, CRP isn't flying solo out there. It's just one piece of a massive, rapid response arsenal collectively known as acute-phase proteins. These proteins are actually always floating around in our bloodstream at really low levels, just waiting. The second your body gets stressed, whether it's an infection, a severe burn, tissue damage, or even extreme psychological stress like schizophrenia, the liver gets the alarm and just cranks up production. They are the ultimate enablers for our immune system, jumping into the fight in ways you probably wouldn't even expect. Take serum amyloid A, or SAA, for example. Just like CRP, SAA spikes like crazy during inflammation. But what's so cool here is how incredibly multi-talented these SAA proteins are at actively prepping the battlefield. First, they shoot up like a flare gun, calling in white blood cells and telling them, hey, slow down, the infection is right here. Then, they actually signal local cells to release enzymes that dissolve the surrounding tissue matrix, literally clearing a path so the immune cells can push deeper into the fight. They even hitch a ride with HDL cholesterol to carry cellular garbage away from the war zone. It's amazing.
And the defensive playbook doesn't stop there. Under assault, your body also massively ramps up production of complement and coagulation proteins. Now, you probably associate coagulation proteins with, stopping a bleeding cut, right? But during an infection, they are literally building walls. They form these tiny, localized fibrin clots to physically wall off a budding infection. They create a biological quarantine zone to trap the pathogens, while complement proteins bind to the damaged tissue so macrophages know what to clear away.
But here's the dark side of this microscopic war. We have to talk about collateral damage. Remember those predatory white blood cells we rely on? Well, they're packed with an incredibly powerful arsenal of destructive enzymes meant to dissolve bacteria. The problem is, in the chaotic heat of battle, those enzymes can leak out. And when they do, they cause massive friendly fire, dissolving our own healthy surrounding tissue. It's basically a biological sewage spill of highly toxic materials right inside your body. Honestly, if left unchecked, the cure would kill you just as fast as the disease. So we desperately need a specialized cleanup crew. And what is absolutely stunning about this is how neatly your body pairs a specific protective protein with a specific biological hazard to stop that collateral damage. For instance, when those destructive enzymes leak from our white blood cells, the body deploys alpha-1 antitrypsin to hunt them down and neutralize them. When tissue gets shredded and releases free iron, which is highly toxic to us but basically an all-you-can-eat buffet for bacteria, ceruloplasmin rushes in to lock it away. And if red blood cells burst, dumping toxic free hemoglobin that could literally destroy our kidneys, haptoglobin and hemopexin team up to safely process it. It is just a perfectly coordinated cleanup effort. And the best part? They know exactly when to pack it up and go home. Remember our first responders, CRP? It has a remarkably short half-life of just 19 hours. Your body knows that these acute-phase proteins are strict emergency measures. They're for rapid deployment, not long-term occupation. So the minute the immediate crisis is contained, and those slow-building, highly specific antibodies finally arrive on the scene, CRP levels just plummet. It efficiently retreats, making sure your body can get back to peacetime operations as quickly as possible. But hey, manufacturing proteins in the blood isn't our only early-stage weapon. Our body actually has one more incredibly dramatic trick up its sleeve to survive that 7-day gap. It literally alters the entire playing field to swing the battle in our favor. It goes full scorched earth. This is probably the most misunderstood weapon we possess, yet practically every single mammal on Earth relies on it to stay alive. I am talking, of course, about pyrexia. The word itself comes straight from the ancient Greek word pyrex, which literally means fire. Now, today, we just call it a fever, and we've been conditioned to think of a fever as the illness itself. Like, if you feel terrible and hot, it means your body is failing. But pyrexia is absolutely not a failure. It is an incredibly complex, intentional, evolutionary superpower. Your body is deliberately setting a biological fire to burn the invaders out. Now, we really need to clear something up here because there is a massive difference between an intentional fever and something like heat stroke. With heat stroke, your body's temperature control has completely broken down. The outside environment has overwhelmed you, your cooling systems have failed, and you need emergency cooling right away. But a fever? That is a highly controlled, tightly regulated response orchestrated perfectly by your nervous and immune systems working together. Your body's completely in the driver's seat, deliberately cranking up the heat to thwart an invading army. So how does this brain hijacking actually happen? Let's walk through it. First, as the battle starts raging, your immune cells release these chemical stimulators called pyrogenic cytokines. Second, these chemicals literally travel up and cross the blood-brain barrier. Third, they lock right onto specific heat production neurons in the preoptic part of your brain. Fourth, these neurons reach into your hypothalamus and physically crank your body's thermostat well above the normal 37 degrees Celsius. And finally, your brain tells your body, hey, you're freezing. That is exactly why you start shivering uncontrollably and your blood vessels narrow. Your body is desperately generating heat to reach that newly elevated thermostat setting. So why put yourself through all that misery? Why the shivering and the sweating? Because tactically, it is a masterpiece. First off, Microbes absolutely hate the heat. At higher temperatures, their enzymes basically stop working, and their reproduction grinds to a halt. Meanwhile, your elevated heart rate becomes a biological superhighway, pumping your white blood cells to the infection site at top speed. The heat supercharges your interferons and cytokines, it throws your macrophages into an absolute feeding frenzy, and it even speeds up tissue repair. You are quite literally disabling the enemy while giving your own troops a massive performance boost. But what is the literal first thing we do the second we get the chills? We reach for antipyretics, medications like aspirin, Tylenol, or ibuprofen. These drugs work by blocking those chemical signals in your brain, forcibly ripping the thermostat back down. Now, to be absolutely clear, extremely high temperatures can be dangerous and absolutely need managing. But considering how perfectly engineered this defense system is, we really have to question our modern instinct to immediately suppress our primary defenses just so we can feel a little more comfortable. When we do that, we are quite literally disarming our own troops. I want to share a quote with you that I think totally flips how we look at feeling sick. Fever is not a disease, but rather a symptom of invaders and a means of combating them. It has its place. That misery you feel when you're in bed, sweating and shivering, that isn't just the infection winning. That is the feeling of a brilliantly coordinated internal army using everything from acute-phase proteins to localized fire to keep you alive during that incredibly vulnerable 7-day gap. So, here's what I want to leave you with. Armed with this new understanding of exactly how hard your acute-phase proteins and your hypothalamus are fighting to protect you, the very next time you feel a fever coming on and that shivering starts, what are you going to do? Are you going to immediately reach for the medicine cabinet to put the fire out, or will you trust the system, embrace the heat, and let your body fight? Thanks for exploring this incredible biology with me today.